Hey guys, in today's video we're going to be looking at inverse functions. We're going to look through a bunch of the different properties but also self-inversing functions as well. We're going to look at their respective properties and some example questions, so like a bunch of example questions to get you guys comfortable with independently solving these problems and also questions. We're going to look at graphing them and yeah, let's get into it. So the first thing that you need to know is what are actual inverse functions. So like the simplest way to put this is let's write inverse functions. So the operations such as like plus and minus, they are regarded as inverse operations, right? The same can be said by multiplication and division. As one undoes, slash does the reverse of a bit bigger of the other. The same principle is seen in when we're dealing with inverse functions, whereby the function y is equal to 2x plus 3 can be quote unquote undone by its inverse function x minus 3 over 2. So for example, let's say that this function here can be described as f of x is equal to 2x plus 3. And the way we denote the inverse function, we do f to minus 1 of x is equal to x minus 3 over 2. How did I get this here? Well, we just set y is equal to 2x plus 3. So then let's make x the subject. So in doing so, we get y minus 3 is equal to 2x. And y minus 3 over 2 is equal to x. Make sure to replace the y with the x. So you switch the y and the x around, so you get x minus 3 over 2 is equal to y. Where y is equal to f of x. Well, no, not where y is equal to f of x. This is just the inverse function now. So this would just be equal to f of x. Okay. So firstly, we need to know one-to-one and many-to-one functions. These are just mappings of functions. So a one-to-one function, a one function, is where for each x value, there is only one value for y. And for each y value, and therefore for each y value, there is one value of x. So equivalently, a function is one-to-one if f of a is equal to f of b only where a is equal to b. So one-to-one functions satisfy both the horizontal and vertical line test. So basically what this means, so for the vertical line test, it means that no vertical line can meet the graph more than once. Graph more than once. And no horizontal line can meet the graph. So for the horizontal line test, line test, no horizontal, can meet the graph more than once. Okay, so what would this look like? So for example, if we had the function f of x is equal to x cubed, so what would this look like? So we can graph this function. Alright, so try to be as accurate as I can. So we know that one-to-one functions satisfy both the horizontal and vertical line test, but how could we actually test if it satisfies both? Well, for the vertical line test, what we would do, we would draw a series of vertical lines across the graph to test if it passes. If it passes, then the maximum amount of times a vertical line passes through the graph will be once. And as we can see, it passes as it's only intercepting the graph a maximum of 1 times, therefore passing. Now, what if you try to do the horizontal line test? Well, that's the same, but we're just doing them horizontally, like that, like so. And we can therefore see that it is both one-to-one, is one-to-one as it is passing both horizontal and vertical line tests. Alright. Now, if we look at, so if a function is one-to-one, is 1 to 1, it will have an inverse function. So it's incredibly important to say that if it is 1-to-1, meaning one x value has one y value, and they don't have any other y or x values, then it will have an inverse function, which we can denote. As f-1. Functions that are not one-to-one are called many-to-one, where these functions satisfy the vertical line test and do not satisfy the horizontal line test. So if you guys don't remember from the last video, one-to-one, the mappings that make a function valid are one-to-one, many-to-one. As discussed in the last video, many-to-many and one-to-many don't work, as they won't pass the vertical line test, therefore fail and are not considered functions. However, one-to-one and many-to-one, they are the two that actually pass. So the relationships that are many-to-one and one-to-one, they are called functions. So if we have many-to-one, the only other mapping of a function that can be possible other than one-to-one is many-to-one, and these satisfy the vertical line test. However, do not satisfy the horizontal line test. So what does a many-to-one mapping actually mean? It just means that at least one y value, one y value has more than one corresponding x value. So this just means that more than one x value can have the same y value, and it will still show a valid function. So let's say the function f of x is equal to x squared. This should be a function that you're all very comfortable with. It's literally just the simplest quadratic that you could possibly have. So if we look at this, we can see, if we draw this function first, we can see it will pass the vertical line test, no problem, like so, with the max interceptions being 1. However, once you start drawing horizontal lines, we can see that it's intercepting at 2 points, which we know that means that it's failing the horizontal line test. But how can we display this algebraically? Well, as we have the function f of x is equal to x squared, well, let's try to substitute some numbers in. Well, so if we have f of x is equal to 4, well, then that means that since x squared is equal to 4, that means, so x squared is equal to 4, that means that x is equal to plus or minus root 4, but x is equal to plus or minus 2. So it's equal to 2, or x is equal to minus 2. Therefore, many to 1, because one y value has multiple x values, whereby f of x, so you would say that f of x is equal to y. F of x is just another way of saying y when we're looking at graphs, so they can be used interchangeably. So here we can see that this y value has multiple x values, where x can be equal to 2, or it can be equal to negative 2. So therefore many to 1. But now here's an important statement. If a function f of x is many to 1, it does not have an inverse function. However, for a many to 1 function, we can often define a new function using the same formula but with a restricted domain. So define new function, I mean, with the same formula but restricted domain to make it a one. If you don't understand this, don't worry, I'll summarize it for you guys and explain this definition. This new function will have okay, so as we know that one-to-one functions, they do have an inverse function as they satisfy both horizontal and vertical line tests. However, we know that many-to-one functions do not satisfy the vertical line test, but do not satisfy the horizontal line test, so therefore don't have an inverse function, right? However, we can manipulate the f of x, we can manipulate the function, whereby we can restrict its domain. The domain is a set number of x values that can be taken by the function. So if we look at the graph f of x is equal to x squared, well, we can see that we could restrict the x domain so it only includes this part here. Whereby if we only include this part here, what would it look like? Well, we have a graph like this, and it passes the horizontal line test and both the vertical line test. And by restricting the domain to just this area here, rather than the entire length here, well, now it's passing both horizontal and vertical line tests, and what it has the same formula, but it's technically a new function, and is able to produce an inverse function now because it's satisfying both horizontal and vertical line tests. Alright, let's look at some. Let's look at the properties of the inverse of function. So properties. This is like really common in IB exams. You typically see them part of a much larger question where you'll be asked to build upon functions. They can range from like 5 to 10 marks, but yeah, properties of. So it's really important that you get these easy marks. 'Cause typically, these drawing and graphing questions are guaranteed marks as long as you remember all the rules and the properties. So if f of x has an inverse function, well, we know this means that it's a one-to-one mapping. This new function is denoted by. You should be familiar with this, like from prior education, like GCSE or something like that. You would see inverse functions. Must tickle line test and has a graph which is the reflection of y is equal to f of x in the line f, or no, y is equal to f, y is equal to x, equal to x, and satisfies both. Okay, so what does this mean? So wait, we should write both. Okay, so this notation here just means f following f of the minus 1x. So what would this look like? So it's f following f minus 1x. They had their equivalent forms. So it has to satisfy both this one here and following f. If you're not sure about this notation, then you can look at my previous video on composite functions is equal to x. So what does these two notations mean? If you see like this circle symbol here, this just means following. So f of the inverse function of f following f of x. So this can be rewritten as f of the minus 1 following f of x. You literally just do what it says and write it in order. Alright, so the function y is equal to x is equal to x is called the identity function. The identity function. Right, as it has its own inverse. So it is its own inverse, and when its inverse is found, x, y coordinates map onto itself. So the function y is equal to x is the identity function. This is why we use it. So to summarize the properties, if f of x has an inverse function, this new function is denoted by f minus 1x and must satisfy the vertical line test. And it will also have a graph which is reflection of y is equal to f of x in the line y is equal to x. So it's a reflection of y equals to f of x utilizing the line y is equal to x, which is the identity function. And it must satisfy f following the inverse function of x is equal to x, and f, the inverse function of f following f of x is equal to x. I think this is much easier to see and when we're doing examples. So I'm just going to go through some examples and highlight the terms. So let's say, wait, let me just try and find an example for you guys. Alright, so this looks like a good one. Alright, so say if x, y lies on f, then yx, so the inverse, lies on the inverse function of f. So how is this done geometrically? Well, geometrically, we use the properties of the inverse function of f of x, which is by reflecting the graph y is equal to f of x in the line y is equal to x. Algebraically, however, we find the formula for the inverse, or for an inverse function, rather, function by exchanging x and y. Alright, so for example, we have this function here. We will typically see this notation in our IB exam, so we'll see, what does this mean? Well, this colon looking symbol just means such that, such that. So what is this read as? Well, this is read as f such that y is equal to 5x plus 2. And what would this become? Well, this becomes, so if we're trying to find the inverse function of this, we would write as f, so the inverse function of f, such that x is equal to 5y plus 2. See, exchanging x and y. This is an example of using algebraic methods, where we just exchange x and y to find the inverse function. Right, so we can also rearrange this to find that. So we rearrange this to find the actual inverse function, which is such that y is equal to x minus 2 over 5. Because it's important to note that f of x is equal to y. Right? So you typically just do it how you would find an inverse function. So where f of x is equal to 5x plus 2, we'll just usually just set y is equal to 5x plus 2, or a random variable, right? Then we'd make x a subject, which is 5x, y minus 2 over 5 is equal to x. Then we would swap x and y to get x minus 2 over 5. And that is your inverse function. Right? So if we're graphing, so I'm going to show you how we would graph this and show it in an exam. So let's graph the two functions. So let's first graph f of x. So f of x is 5x plus 2. Wait, that was a bad line. Let me try it again. That's a bit better. Alright, so what are we trying to do now? Well, we need to use the line y is equal to x to reflect this function, of course. So you can see that this has y-intercept 2, right? Well, what do you think is going to happen now? Well, now the vertical axis intercept now becomes the horizontal axis intercept for the inverse function, right? So what can we do? Well, so we use the line y is equal to x as our reflection line, or reflection axis of reflection. So just imagine this dotted line is y is equal to x, passing through the origin, of course. And what do we do now? Well, we just simply reflect the lines. So this would be f minus 1 of x. This is f of x. As we can see, it's a clear reflection. And so we can prove that y is equal to f, the inverse function of x is an inverse of y is equal to f of x, as it is also a function and it is the reflection of y is equal to f of x in the line y is equal to x. So, but it is important to note that the inverse function of x is not equal to the reciprocal of f of x, okay? And so it can be stated that if f of x has an inverse function, so that we denote as f minus 1 x, then the domain of the inverse function of f is equal to the range of f, and the range of the inverse function, so f of minus 1, is equal the domain of f. It's also important to know that the horizontal axis intercept becomes the the vertical axis intercept of f of x becomes the horizontal axis intercept of f minus 1 at x. So let's say we have another question that says consider f such that x converted into 2x plus 3. So first we can look at this notation. This is such that, and this arrow here just literally just means is converted into. So this can be written as, into a more comfortable form that I'm sure most of you are familiar with. F of x, the function of x, is equal to 2x plus 3, which is also equal to y is equal to 2x plus 3. I think it's easier just to look at it in this form, just so we can substitute numbers in, and it's more clear on how we're writing the inverse function as well. So we'll typically, so it's completely fine to get rid of this form here and just convert it into here. So, as they do just mean the same thing. So let's just say part A of this question is saying on the same axes, graph f of x and its inverse function. Inverse function. So there's a couple of ways that you can kind of cheat when you're doing this. Well, so f of x, it has coordinates in the form of x and y. Well, for f minus x, it would have these same coordinates but in the form of y, x. So let's just say random coordinate 2, 7. This point, the inverse, would be 7, 2. This would be how it would be reflected through the line y is equal to x. And also, all the vertical axis intercepts become the horizontal axis intercepts for f minus 1. So, okay, I'm going to draw it first. So, what's f of x? F of x is equal to 2x plus 3. So, we would simply just draw the function 2x plus 3. So, 3 is up here. That's where it intercepts. And we'll see, we draw it like so. Just imagine it's intercepting here. Then we also have y is equal to x, which is the line we're using to reflect. And alright, so this point here is 0, 3. Sorry. And the point, so this is where it intercepts the y-axis. So what's going to happen now is that where f dash x, the inverse function of f of x is going to intercept the x-axis is going to be at 3, 0. 3, 0. Whereby we can draw it like this. And it forms a reflection of the line. And okay, so let's say we have an imaginary point here. So the way you can test if you've actually drawn it correctly is if you have a point here, I'll use the same example, that this is going to be like 2, 7, right? Actually, that won't make sense. We could do, yeah, 2, 7. 2, 7 seems alright. So if you have a point 2, 7, well, we need to make sure that we have the inverse of these coordinates somewhere on f of x, f dash of x, right? So let's say, so somewhere on this line has to be the reverse coordinates of this point. Because, so that means that somewhere here, there has to be like 7, 2. Because as we remember, that if f of x, so if xy lies on f, then yx must lie on the inverse function of f. Okay? So if 2, 7 is on this line, somewhere on this line, 7, 2 therefore must be on this line. So if something like 1, 5 was on this line, so let's just say like 1, 5 was on this line, that means that on f, the inverse function of f, 5, 1 must be somewhere on this line. Alright? So you can do these tests and these small little tricks to make sure that you've got it right. Because if you don't have the same values, then, or the inverse of each value, or coordinates rather, then it would be incorrect. So now let's find. So let's say the part B is asking you to find the inverse function of f using coordinate geometry of the gradient of y is equal to the inverse function of x from part A. Alright. So f dash 1 of x, so the inverse function of x. So we've already drawn this function here, right? We've already drawn the inverse function and we've already checked that it's correct. So what would we do? Well, we know how to change the we know how to calculate the gradient. So we just pick two coordinates on the line. So let's just say we pick 0, 3, 0, and let's say 7, 2, because well, we've already been working with those values. So let's say we have two values. So we have 3, 0 and 7, 2. Right. I do advise using axes intercepts. It's just easier to calculate, and it's more likely that you've got the correct value for that. Because everyone's drawings will be different, but everyone's intercepts will be the same. So it's important to use an intercept preferably. So we know it's is a change in y over the change in x. So we just do 2 minus 0 divided by 3 minus 7. And this gives you 1 half. Right. And then we can say that its equation is y minus 0 and x minus 3 is equal to a half. Therefore, y is equal to x minus 3 over 2 by making y the subject, and hence f, the inverse function of f is equal to x minus 3 over 2. So we've therefore found the value, or the gradient of the inverse function, so the equation for the inverse function using the gradient and coordinate geometry. Well, how have we done this? So we've used the gradient, which we set as 2 minus 0 and 7 minus 3 to get a half. And, well, if you look here, we can take the value of the constants, 2 and 7, and substitute them with y and x, so the variables y and x. Because we know that the intercepts, they're going to remain constant no matter what. Like, the intercepts aren't going to change off the inverse function of f of x, right? So instead of writing 2 and 7, we can just substitute that with y and x. So in effect, we get y minus 0 over x minus 3. And the gradient won't change. Since it's a linear function, the gradient is constant throughout. So we can just simply set this to half the gradient that we found using 2 and 7. And therefore, we achieve that y by making y the subject. So we can times by x minus 3, both sides by x minus 3 to cancel out the x minus 3 and get a half, right? Sorry about that, guys. My recording stopped. So now we're at a point where we have, so we found the gradient where 2 minus 0 over 7 minus 3 is equal to a half. And therefore, 2 and 7, they're just constants. We know the gradient is going to stay the same because it's a linear function. And we know 0 and 3 are the same because it's an intercept. So that point can't change. So we can get an expression for this where instead of 2 and 7, we can substitute with y minus 0 and x minus 3. That's a general formula for the gradient, which is equal to a half. And therefore we can get y is equal to x minus 3 over 2. And as this is the gradient for the inverse function, we can say that y is equal to the inverse function. So f is equal to x minus 3 over 2. Alright. So now part BII of this question would be show variable interchange. And using variable interchange, find f of x, the inverse function of f of x. Well, how can we do this? Well, we know that f is equal to y is equal to 2x plus 3. And therefore, f, the inverse of f is x is equal to 2y plus 3. You know, just swapping x and y. Well, therefore, x minus 3 over 2 is equal to y for the inverse function. And hence, f1 of x is equal to x minus 3 over 2. This is using variable interchange, as we're interchanging both x and y to get a function for f, the inverse function of f, and then using that to find the actual expression for it. Now, part C would be stressing one of the other properties of the inverse function of f, where we would have to state that f following f minus x is equal to the inverse of f following f of x, and that this is equal to x. So what does this actually mean? Well, this just means that f following the inverse function of f of x, and the inverse function of f of x following f of x. So what does this look like? Well, f following the inverse function of f of x is the same as writing it like this. And then this is the same as writing the inverse function following, so inverse function following f of x. There we go. So how would we write this? Well, we can solve it in stages, right? So firstly, let's solve this side first and just express this in a way that we can comfortably show that they're both equal to x. Well, so f following the inverse function of f of x. Well, what is the inverse function of f of x? Well, we found that to be x minus 3 over 2. So as the inverse function of f of x is equal to this, well, we can substitute this function into here as they're both equal. So we actually have f following x minus 3 over 2. Now we can just solve this as a normal function question. Well, what is the expression for f? Well, f is equal to let's see here, it was equal to 2x plus 3. And we know how to solve this function, but this just means that the function of x is now x minus 3 over 2. So we can just substitute this for the function for x. So we get 2 multiplied by x minus 3 over 2 plus 3. And leaving us with 2x over 2 plus 3. So we get x minus 3 plus 3. Well, minus 3 plus 3 is 0, so we just get x. So we know that this function here, that this expression, is indeed equal to x. Now looking at the right one here. So we have the inverse function of f following f of x. Well, what is f of x? It's 2x plus 3, right? So we can, instead of writing f of x in here, we can just write what it is equal to, 2x plus 3. Now we just substitute this into the inverse function for x. Well, what's the inverse function? X minus 3 over 2. So we can substitute, as the function of x now is 2x plus 3, we can take that and put it in here. So we have 2x plus 3 minus 3 over 2, leaving us with equal to 2x over 2. The 2's cancel and we get x. So they are both indeed equal to x. Now let's go through another one. So we have f such that x. So this is a new example. Example 2. So we have f such that x converts into x squared. Alright. What can this be written as? F of x is equal to x squared. So this part A might be explain why this function has no inverse function. Well, we know that we can work backwards, where we know that a function has an inverse function where it passes both vertical and horizontal line tests. So we can check for this. Whereby if it passes both, then it's 1 to 1, and if it doesn't, then it's many to 1. So let's draw the graph of y f of x is equal to x squared. So we see this now. So let's try to do the vertical line test. Okay, great, passes that. Now let's try to do the horizontal line test. If you look at that, it's intercepting at multiple points, therefore failing, and is many to 1. Therefore, many to 1 as fails horizontal line test. And hence has no inverse function. Right. So the second part B would be, does f such that x can be converted into x squared, which we know just f of x is equal to x squared, where x is function. So what it's saying is, does f of x equal to x squared, where x has to be greater than or equal to 0, have an inverse function? Well, we do know that one way to make it so a many to one function does have an inverse function is to make it 1 to 1, and this is done by restricting the domain. So we have to test this out. So what does where x has to be greater than or equal to 0 mean? So let's draw the function of f of x is equal to x squared. This looks something like that. Wait, sorry. Bloody hell, man. There we go. Alright, so this is where x has to be greater than 0. So what does this mean? This means that we're only including whereby the x value is greater than 0. So that'll be this section here. So what we can do, we can get rid of this. So this is now invalid, as it does not fit the restriction. So what do we actually have now? We have this, where we can clearly see now that this does pass the horizontal line test. And it already passed the vertical line test, we already know that. So, yeah, now it does have an inverse function. So, and therefore, 1, 2, 1, passing both vertical and horizontal line test. Alrighty. Now let's look at part C. Find the inverse function of f of x for f such that x is converted into x squared, where x is greater than or equal to 0. Well, okay, so we see that f is defined by f of x or y is equal to x squared, where x is greater than 0. I think when you're trying to calculate the inverse function, it's much easier to work out all in y's and x's and then convert it back into function form. So I think we're going to do that. So therefore, f minus 1 of x is defined where where x squared, x is equal to y squared. So if you don't know what I've done there, we know that for the inverse function, we just swap the x and y's around. So if you can see here, y is now taking the place of x, and now x is taking the place of y. Hence, however, the domain and range switches now, whereby the domain of the inverse function of f of x, domain, equal to range of the original function, and range is equal to domain of f of x. So we can see that the domain of f of x is defined by this function here. So that would mean that instead of the domain being greater than or equal to 0, the range would have to be of something like that. We would use y instead because we're looking at the range now. So what would this look like? So we can see that x is equal to y squared. So this is for f minus 1 of x, where y is greater than or equal to 0. So then we can state that y is equal to the square root of plus or minus x, where again y is greater than or equal to 0. Therefore, so what does this mean? Well, as it's plus or minus x, there's two values. However, through this restriction where y has to be greater than or equal to 0, x cannot be negative. Therefore, we have to have y is equal to root x, and we reject the solution negative x, as y has to be greater than 0. So, therefore, we know that y can be substituted by that, by the inverse function of x. Therefore, equal to root x. Now, let's sketch the function of, so part D would be sketch y is equal to f of x and y is equal to x. Okay, so, and y is equal to the inverse function of x for f in both part B and C. So, what did we get? So, we know that for f of x is equal to x squared, where x is greater than or equal to 0. And we know that the inverse function of f of x is equal to the square root of x, where y is greater than or equal to 0, right? So how would we draw this on the point? We got these from parts B and C, by the way, if you guys were wondering. This is what we literally just worked out. And B is from all the way up there somewhere. So how do we draw this? Well, we know that we need to have our identity function, which is y is equal to x, which is what we use to reflect the function. So we'll draw that here. Remember, guys, you should use a ruler, but I'm just doing this for speed. Okay, so we have the function y is equal to the square root of x. What would this look like? Well, this where y has to be greater than or equal to 0. Remember that fact as well. So this would look something like this, like that. Remember to draw an arrowhead to show that it's a continuous function, because it always is going to infinitely continue in that relative direction. Now let's look at y is equal to x squared. Well, that is simply, I mean, that looks like this. That. I think also, don't be shy to start substituting in values and switching the coordinates for the inverse function of f of x. If you're not comfortable getting it correct the first time, that's completely fine. Okay, now we're going to move on to self-inverse functions. So a self-inverse function is any function for which has an inverse and whose graph is symmetrical. Wait, spell it wrong. About the line y is equal to x is a self-inverse function. So the function f of x, is equal to x is the identity function. We know this function here, which is y is equal to x, which we use as a reflection axis, or the axis of reflection, to show the f of x and the inverse function of f of x. That's an example of a self-inverse function. The function f of x is equal to 1 over x, where x cannot be 0. Well, we know y can't be 0 because 1 over 0, any number divided by 0 is equal to undefined. So it's also a self-inverse function. As f is equal to f minus 1. So basically, what it means by symmetrical about the line y is equal to x is that when you're trying to find the inverse function or try to graph it, right, they produce the same graph because they're both equal to each other. So let's try this. You can check your graphs utilizing like online graphing services, or you can use your GDC calculator, whichever of the two works out. So let's start off with the first question. So I'm going to go through a bunch of questions. You can check these using like Desmos or something like that, and then yeah, so that you've done it correctly. So so the first part of this question, part A, it will go something like this: on the same graph, or same set of axes rather, graph y is equal to x, and so y is equal to f of x, and y is equal to f, the inverse function of x. Alright, so how do we go about this? Wait 1 second. Wait, I think this is the wrong question. Yeah, okay. Yeah, no, this is fine. So, part A, on the same set of axes, draw y is equal to f of x and y is equal to the inverse function of x. So, let's say our first function is f of x is equal to 3x plus 1. Alright, how do we do this for this question? Well, So we know f of x, 3x plus 1, passes through 0, 1, and negative a third, 0. As these are two axes intercepts, so how would we find this? So I'll show you guys how I found this. So 3x plus 1, we know that c, this graph's in the form of y and mx plus c. We know that c is the y-intercept. Therefore, we know that at the y-intercept, x is 0 and y will be c, right? To find the x-intercepts, however, we know that y is equal to 0 on the x-axis, as it's on level with the origin line where y is 0. So we have 0 is equal to 3 x plus 3 plus 1. I mean, we solve for what x. We get minus 1 over 3 is equal to x. Where y is 0, so we get negative a third 0, and here x is 0, so we have 0, 1. All right. So we can graph these two using these values, and as they're linear functions, you can typically just substitute values in, and then you'll get the correct answers. So y is equal to f of x. Let's do that one first. But first, you have to draw identity function y is equal to x. So we can see that that f of x intercepts at 0, minus 3, 0. That's about here, 1 over 3, 0. And we know that its y-intercept is 0, 1. So we can just write that all the way up here to say this is 1. So the gradient is 3x, 3 I mean. So we can draw it like so. It's a bit messed up, wait. Alright, there we go. Yours should be much straighter than mine if you're using a ruler and everything. So we know that for the inverse function of x, all the coordinates they swap. So instead of the form of xy, they're yx, right? So let's take that for example. So we know that it has intercepts 0, 1, and negative a third, 0. So we know that this is for f of x. So what would it look like for f minus x? Well, we know that for f of x, it's in the form x, y. So for the inverse function of f of x, it'll be y, x, like that. So what would it look like for the inverse function of x? Well, it would be, instead of 0, 1, it would be 1, 0. And instead of 0, negative a third, 0, it'll be 0, negative a third. And then we can draw this on to our axes. So we can draw this like so. So this is going to be 0, negative a third. And then 1, 0 would be here. So we'll draw this on. So, and it's intercepting there. And that'll be our intercept. Right. So now we're trying to find the inverse function of f of x using coordinate geometry and the gradient of the inverse function of f of x from this graph here that we've just drawn. Right. So, alright. So how would we do it using the gradient? Alright. So using both the gradient and coordinate geometry, we know that y is equal to f, the inverse of x. And this has the gradient. So we know that the gradient is changing y over changing x, so we can just pick 2 points. Well, we have 2 points here. They're both intercepts, and we just might as well just use them since we've already worked them out. So what are the y values? So we have negative a third, minus 0. These are the 2 y values. And these are the 2 x values. Over 0 minus 1. So we get negative a third over minus 1, which is just equal to a third. So therefore we get, so y is equal to y is equal to x minus 3 over x minus 1 over 3. How did I do this? Well, we know that, so the gradient is minus a third minus 0 over 0 minus 1, and that will give you a third, right? Well, we can take these y and x values and substitute them for y and x. So negative a third is the first y value, and 0 is the first x value. So what do we get? Well, we get y minus 0 over x minus 1, and this is equal to a third. Alright? So then, making y the subject as y is equal to the inverse of f of x, well, we can just do this. We can multiply both sides by x minus 1, so we get x minus 1 over 3. Therefore, leaving us with that the inverse function of f of x is equal to x minus 1 over 3, using graphical methods. So, part 3 to this question would look something like this. Find the inverse function of f of x using variable interchange. How do we do this? Well, so f minus 1 of x using variable interchange. So we have both f of x and expressions for both, right? And we know that variable interchange is literally just substituting different values and switching them around. So, well, we have f is equal to y is equal to 3x plus 1. Therefore, using variable interchange, we know that f of minus 1 is equal to x is equal to 3y plus 1. Alright? So, now we can just state that, therefore, x minus 1 is equal to 3y. Therefore, y is equal to x minus 1 over 3. And where y is equal to the inverse function of f of x, therefore minus 1 of x is equal to x minus 1 over 3. As we know, we can do variable interchange as it's the inverse of f of x, therefore we can just switch the variables around. Nice. Now let's do another one. Let's look at another example. So let's say we have f such that x converts into x plus 2 over 4. Right. So this is f such that x is converted into x plus 2 over 4. I'm just trying to make sure that you guys know the notation, and this can be written as f of x is equal to x plus 2 over 4. Right. So now let's try to graph both of these using the identity function, and let's try to graph both functions. So what would this look like? Well, we know that we've got a value of f of x, which is x plus 2. So how do we do it? So we'd find the gradient, and we would find the x-intercepts for this equation. So we know f of x is equal to x plus 2 over 4 can be written as y is equal to x plus 2 over 4. So how do we find the x-intercept for this function? Well, we know at the x-intercept y is equal to 0, so we can just do 0 is equal to x plus 2 over 4, where 4 times 0 is 0, is equal to x plus 2, so negative 2 is equal to x. And we can do the same for y, but we know that at the y-intercept, x is equal to 0, so we have y is equal to 0 plus 2 over 4, therefore y is equal to 1 half. So to find the coordinates for the x-intercept would be 2, 0, as we know y is 0 at the x-intercept, and the intercept for y would be 0, a half, as we know x is 0 at the y-intercept. Alright, so we know that f of x has to pass through these 2 points here, as they're the intercepts, right? So what can we do? Well, we can easily just graph this function now. So drawing our identity function first, which is y is equal to x, and the axis of reflection, we could then write both our points here, minus 2, 0, and 0, a half would be somewhere up here. So using this, we can simply just draw it through. like so. Now, as we have these coordinates for this is x-intercept and y-intercept. Okay, I'm gonna draw it. I'm gonna write them down here just so we know f of x has intercepts 0, a half, and -2, 0. And we also know that the inverse function. So therefore, we know that the inverse function of f of x, we switch the y and the x values. So the intercepts for the inverse function of x would be equal to a half, 0, and 0 minus 2. And then we can easily draw this function by labeling its intercept. So we have half 0, which is around about here, half. And then we have 0 minus 2, which is down here, and we're down here. Then we can draw the function. In an exam setting, you would preferably want to substitute a couple of points in and then get the answer, but I think this should be fine. As long as you're straight and you have all the intercepts labeled and you've clearly intersected both of them. Alright, part 2. Find the inverse function of f of x using coordinate geometry and the gradient of the inverse function of f of x. So how do we do this? Alright, so what would be the gradient of the inverse function of f of x? Well, we know that the gradient is the change in y over the change in x, and we can use two different points to do this. We can use just the intercepts, as we already have them, to stop us from having to work out and find two other points. So what would we do? How would this be written? So we would have minus 2 minus 0 divided by 0 minus a half. And we know that this would be equal to 4. Because minus 2 divided by minus half is the same as saying minus 2 times by minus 2, and that gives you 4. Alright, so its equation, therefore, in just a general form, would just be y minus 0, x minus a half, right? So that is equal to 4. Now we just solve for y, so we get y is equal to 4x minus 4 over 2, y is equal to 4x minus 2. And we know that y is equal to the inverse function of f of x, so we say f is equal to 4x minus 2. Now, part C would be something as follows. So part C would probably be something like, find the inverse function of f of x using variable interchange. And we know that variable interchange is just simply just swapping x and y values. So we have a function for f of x, which is equal to x plus 2 over 4. So f of x is equal to y, which is equal to x plus 2 over 4. Right. And we also have an expression for the inverse function of f of x, which is this right here. So we know that the inverse function of f of x is equal to x is equal to y plus 2 over 4. How do we know this? Well, we know that f of x is equal to y is equal to x plus 2 over 4. So, using variable interchange, where we switch the variables around, because they're inverses of each other, we can switch the two variables around. X is equal to y plus 2 over 4. And now we just solve for y, because we know that y is equal to f dash 1 of x. So what do we get? X is equal to y plus 2 over 4. Therefore 4x minus 2 is equal to y. And that's your answer, where y is equal to f minus 1 over. And therefore f, the inverse function of f is equal to 4x minus 2. I hope you guys understand, and that'll be it for today, and thank you guys. See you in the next one.